Hello everyone, my name is Sultan Almakdi. I'm a PhD student at University of Arkansas in the United States of America. Today I'm presenting my paper, which is designing a bit-based model to accelerate query processing over encrypted databases in the cloud. Nowadays, people and organizations have started moving toward cloud computing as a storage, and that's because it provides high computation speed, massive data storage at affordable prices. Also, cloud providers provide database as a service, but the problem is once the data outsourced to the cloud, the user will lose the control of who is accessing the data. So the data leakage is the primary concern for people and organizations. Data encryption is an effective solution to solve this matter. However, there are challenges to execute queries over encrypted data. For example, searching for a numeric range of data. There are different proposed encryption algorithms to encrypt data before outsourcing. One of them is using a deterministic algorithm. Deterministic means the plain text will always have the same ciphertext, and another kind of encryption algorithm is order preserving algorithm, and this kind will preserve the order among numeric data. Another type is using homomorphic encryption algorithm, and also this kind of encryption is good for encrypting numeric data. However, privacy leakage could even happen when the data are encrypted using the above algorithms. Here is some of the related work. One of the most famous encrypted database systems is Crypt database, and the idea is based on encrypting each data item with more than encryption algorithm. They call it onion layer encryption. Another area is data packetization, where data or encrypted records are divided to multi-packets. Another solution is using multi-cloud data fragmentation, where the database is distributed among and across clouds based on the security level. Also, more than one work has been done using full homomorphic order preserving encryption, and this type of encryption will enable cloud provider to execute arithmetic and comparison operators. The objective of this research is to use a randomized encryption algorithm to encrypt the data. The randomized encryption algorithm means that the plain text will never have more than one identical ciphertext. So that is challenging when it comes to execute queries over encrypted data. So the aim of this model is to minimize the range of retrieved encrypted records from the cloud while ensuring the maximum level of the security at the cloud. So also we're gonna facilitate this model to enable or to support executing queries over encrypted numeric and textual data. Here is the system architecture. We have the cloud, and then we have the query manager that is the main component in our model, and it works as an intermediator between the users and the cloud. The query manager could be a light software for single users or a trusted server that resides in the private cloud for organization or companies. The function of the query manager is to do encryption, decryption, query translation, and communication with the cloud. This will leave the minimal work for Partitioning tree and the encoding method. The query manager will store a partitioning tree for all partitions of all sensitive attributes for each encrypted table. So each table will have sensitive columns, and each sensitive column will have different partition or more than one partition. For example, salary could be partitioned to two partitions. The first partition will be less than 10,000, and the second partition will be greater than 10,000. So the more partitions we have, the faster query processing we get. So our model is efficient when we have more partitions. So we encourage table owners to define more partitions for their tables. And before moving to the encryption process, the query manager will create a bit vector, its length equal to the total number of the subnodes in the third level of the tree, and each bit in the bit vector is mapped to a partition node from the third level. So the first bit in the bit vector is going to be mapped to the first partition, the second bit, second partition, and so on. Then initial the bit vectors to 0, and then move to parsing process, which takes each value, then look up the partitioning tree and see which partition it falls under. Then if it falls under partition 1 or 2, set the bit that mapped to this partition to 1. And we use those bit vectors to retrieve only set of the encrypted record from the cloud. How to store the bit vectors? We avoid storing them locally at the query manager because we need like more memory to store them. So we're gonna migrate them to the cloud. So we will have an additional column to store those bit vectors in each table. So the encrypted table will have an additional column. We call it reference column, and we append each record's bit vector to next to the record. Also, we use AES-SIV to encrypt the name of tables and columns name to ensure that the cloud provider can learn nothing from our data. Here's an example. Suppose a user wanna encrypt a table called employee, and let's say that name, social security number, rank, and salary are the sensitive columns and must be encrypted. Now suppose that the owner predefines the partitions as in this tree, so the name gonna be partitioned by the name's first letter, and we have, for example, here 3 partitions. We could have 4 or 5, but suppose here the user decide to have only 3. The social security number gonna be partitioned by the social security number last digit, could be partitioned by the first digit. Same thing for rank and salary. Now before moving to the encryption process, the query manager gonna take each record and parse it to get values and create a bit vector for it based on the tree. Then encrypt the name of the table and the name of the columns. So we don't have like the an attribute called the name here. We encrypt it using AES-IV, which is a deterministic encryption algorithm, and then encrypt and insert the new encrypted data. We keep insensitive data or non-sensitive data plain here, and we append each bit vector next to the encrypted record in the reference attribute. So the reason we encrypt the names of the header of the attributes is to ensure the maximum level of security and to prevent any inference attack that could result with the presence of bit vectors. So the user just send queries and get results. The query manager is responsible for maintaining the trees, data structure, encryption, decryption, executing queries over decrypted data. To illustrate this, suppose we have the following query: select everything from employees where name is Alice and rank is secretary. So the query manager gonna look the corresponding data structure and find both name and rank are sensitive. Then to translate the query manager does the following: find the number of each partition and convert it to a binary representation. So Alice is belong to partition number 1, so the binary representation of 1 is 1. Secretary is belong to partition number 7, so we take the power of 2, so it's 128. Encrypt the table. Then the query manager gonna encrypt the table's name using AES-IV. Then translate the query as following: select everything from CT where reference, which is the name of the last column, where reference at position 1 is greater than 0, which means is set, and reference at position 128 is greater than 0. Then this will let the query, the cloud provider send back any record has those bits set. The supported query, we enable this model to execute select, project, insert, alter, update, and delete operations. Also, we support count, max, and minimum, set operations, union, and intersection, and join. For more details about those operations, please refer to our paper. It's available in the proceeding. Experiment and evaluation. We used Java to simulate the function of query manager, MySQL at the user side, and as a cloud provider, we used our university server dataset. We used 2 tables, one with 10,000 records, the second one with 20,000 records. Those tables are randomly generated. Each table has 6 attributes in total. 4 are sensitive, 2 are non-sensitive. In this table, we can see that the more clauses in the query condition, the less retrieved records from the cloud. Also, and operation intends to narrow the range of retrieved encrypted records more than OR operation. This figure shows the delay when the query condition has 3 clauses. The delay is neglected when compared with retrieving and decrypting the whole records. This chart shows the percent of reprocessed tuples at the query manager after the decryption process, and most of this is to remove the duplication from the decrypted data. Here we can see the latency of executing aggregation operators. We can see that our model experiences more delay when the aggregation operator is based on a range partition domain. In conclusion, we designed a model to provide the highest level of security and is efficient in the same time. As a future work, we're gonna extend this model to support arithmetic operation like addition, minus, etc. Thank you so much.